These are the notes for section 4.8 day 2 for pre-calc. We are studying simple harmonic motion. It says because of their periodic nature, the sine and cosine functions are helpful in describing the motion of objects that oscillate, vibrate, or rotate. For example, the linkage in figure 4.94 converts the rotary motion of a motor to the back and forth motion needed for some machines. When the wheel rotates, the piston moves back and forth. If the wheel rotates at a constant rate of omega radians per second, so circle that, highlight that, omega is going to stand for our rotational speed in radians per second. It says the back and forth motion of the piston would be an example of simple harmonic motion and can be modeled by the equation of the form d equals a cosine omega t. Now here we're using cosine, but you'll see in a few minutes we could also use sine. Our restriction here is that our angular or rotational speed must be positive. Omega must be positive. A stands for the radius of the wheel, and d is the directed distance of the piston from its center of oscillation. For simplicity's sake, we will define simple harmonic motion in terms of a point moving along a number line. So a point moving on a number line is in simple harmonic motion if its directed distance d from the origin is given by either d equals a sine omega t or d equals a cosine omega t, where a and omega are real numbers and omega is positive. The motion has frequency omega divided by 2 pi, which is the number of oscillations or cycles per unit of time. So frequency will be cycles per second, for example. All right. And notice here, omega divided by 2 pi. When we did our graphing of sines and cosines, instead of the omega, we used to have the letter b in there, and that was in our frequency formula. We had b divided by 2 pi. So it's the same formula, they're just replacing b with omega. Period would still be 2 pi divided by omega, or 2 pi divided by b, and a is still our amplitude. Okay, so for example 5, it says in a mechanical linkage like the one shown in figure 4.94, a wheel with an 8 centimeter radius turns with an angular velocity of 8 pi radians per second. Now I'm going to explain how they're getting the labels in this picture, but I want to pick out the two numbers that were given. We have an 8 centimeter radius, and if we remember from our formula, they said the radius was our amplitude. So we know a equals 8. And then they told us an angular velocity of 8 pi. That is going to be our omega. All right, so in our picture over here, our circle, we have this point P that is rotating around the wheel. As it rotates further and further counterclockwise, this angle gets bigger and bigger and bigger. And it's rotating at a speed of 8 pi radians per second. So if we've gone t seconds, this angle has opened up a distance of 8 pi t. So our angle here for theta is going to be 8 pi t. Now, pretend we do not know this piece right here. Let's just call this an x for that side dimension. If we were to figure out what x equals, we have a triangle with a radius or a hypotenuse of 8, and we are looking at the adjacent side. So we could say the cosine of that angle is x over 8, or 8 cosine theta equals x. And now if we substitute in our value for theta, we have 8 cosine of 8 pi t equaling x. And that's where that came from. So the distance that this point here is moving on a number line, that position it's in, that d value, is going to be based on this equation. D equals 8 cosine of 8 pi t. Okay, so they are asking for the frequency. Frequency, we had a formula. We said frequency equals omega divided by 2 pi. And since omega is 8 pi, when we divide this, we get a frequency of 4. All right, so we have 4 cycles per second. Now, if we look at the picture over here, notice the window they're giving us. T is time, that is our horizontal axis. Okay, so this is time. And we are going from 0 to 1 second. So all of this is happening in 1 second. Our D value is this axis, and it says that we are going from -10 to +10. So our tick marks are going by 2, so you'll see here that we're starting at 8. All right, so that point is moving back and forth, oscillating like it is in this cosine curve. However, it's not moving to the right, it's just oscillating back and forth in the same line. All right, if we were asked for the period, remember that is just the reciprocal of frequency, or 1/4. So we have 1/4 of a second per cycle. So if we look over here, this is 1 second, and you'll notice that we have 4 periods of that cosine curve. Okay. Now, part B says, what is the distance from the starting position t equals 0 exactly 3.45 seconds after we start? Let's go back to our formula up here that we had in green. We said D equals 8 cosine of 8 pi t. We have 2 different t values that we want to compare. We want to know at time 0, and we want to know at time 3.45 seconds. So dumping that into our equation, D equals 8 cosine of 8 pi times 0, which is just 0, and the cosine of 0 is 1, so our distance is just 8. Okay, over here we have to plug in 3.45 for time, so our distance equals 8 cosine of 8 pi times 3.45. Grabbing your calculators, typing that in, we get a distance of 2.47. I think it was 2.472. So when we are comparing the difference from starting position here to where we end up, the difference between those two is going to be 5.528. And that would be centimeters. All right, example 6. It says a mass oscillating up and down on the bottom of a spring, assuming perfect elasticity and no friction or air resistance, can be modeled as harmonic motion. If the weight is displaced a maximum of 5 centimeters, find the modeling equation if it takes 2 seconds to complete 1 cycle. So assuming that our spring is at neutral position, all right, we're starting at a displacement of 0. This would imply that we're going to use a sine equation. Okay, and in our equation we need then D equals a sine omega t. Well, what is our A value? That is our displacement, and it says we are bouncing here 5 centimeters that way, 5 centimeters that way, so our A value would be 5. Now, we have to figure out omega. So now we go back to the other piece of information they gave us. They said it took 2 seconds to complete 1 cycle. That is the period of our graph, all right? Seconds per cycle, how long it takes us to complete 1 full period. So frequency would be the reciprocal of that, or 1/2. So now we can say, well, frequency equals omega divided by 2 pi. If we multiply the 2 pi over to the 1/2, we find that omega equals just 1 pi. And now we can dump that in to get our overall equation. And our last example, it says if we know that the musical note A above middle C has a pitch of 440 hertz, how can we model the sound produced by it at 80 decibels? Couple things to know about sound. When they give us something like this with hertz, that is the frequency. All right, so we have 440 hertz That's the frequency, which is omega divided by 2 pi. So when we solve for omega, we get 880 pi. The other thing to know, when they give us a decibel or a loudness, the loudness is equal to the amplitude in our equation. So we know that A has to be 80. So the overall equation for this, D equals 80. And we are going to use sine because at time 0, there is no sound. So we are starting at 0. So 80 sine of 880 pi t. Okay, for your assignment, yesterday we had done the questions up through number 22. So you have 3 more to do here, 27, 29, and 31. You need to complete this word problem. And then I'm going to have you start review day 1's assignment. That is a half sheet that I'll pass out to you.